Namaskaram. In this session, we will discuss about binomial series. That is a tailored series of a special function 1 plus x raised to m. These are the solutions of last homework. Some of the useful Maclaurin series are okay. Find the Maclaurin series of 1 plus x raised to m, where m is a real number. We know that Maclaurin series is given by the formula f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial into f double dash of 0 plus etc. Okay, in this case, our f of x is equal to 1 plus x raised to m. So f of 0 equal to 1 raised to m, that is 1. Then next we have to find f dash of x. And what is f dash of x? That is m into 1 plus x raised to m minus 1. So what about f dash of 0? When x equal to 0, this is m. Okay, similarly you can find f2 and f3 like that. So f2 of x is equal to m into m minus 1 into 1 plus x raised to m minus 2. So f2 of 0 equal to m into m minus 1. Okay. Okay, continuing in this way, what about f3 of 0? Third derivative at 0. Yes, it is m into m minus 1 into m minus 2 and so on. Okay, so now you are ready to write the Maclaurin series of 1 plus x raised to m. So 1 plus x raised to m is equal to f of 0. Here f of 0 is 1. So 1 plus f dash of 0, here it is m. So m by 1 factorial into x, right? And plus x square by 2 factorial. Instead of f2 of 0, this become m into m minus 1. Okay, similarly, this is the third term, x raised to 3 by 3 factorial into f3 of 0. Here f3 of 0 is m into m minus 1 into m minus 2 plus etc. So this is the Maclaurin series expansion of 1 plus x raised to m. Okay, suppose we consider a special case. Suppose m is a positive integer. Suppose m is a positive integer. Then what about the mth derivative? What is fm of x? If you continuing in this way, what about the mth derivative? So mth derivative become m into m minus 1 etc. up to, for second derivative it is up to m minus 1. So for mth derivative this become m into m minus 1, right, into 1 plus x raised to, this is m minus 2. So in the case of, this is for second derivative. Okay, so in the case of mth derivative this become m minus m, and this is 1 plus x raised to 0, that is 1. Okay, so this mth derivative become m into m minus 1 etc. And what about m minus m minus 1? This is 1. So mth derivative become m into m minus 1 etc. It is decreasing and up to 2 into 1, and this is nothing, this is our this is our m factorial. So if m is a positive integer, then fm of x is equal to m factorial. So what about fm of 0? That also m factorial. Okay, here mth derivative is a constant, it's an m factorial. So what about fm plus 1 x and etc.? All the derivatives after this m, all the derivatives are 0 because it's a constant. Okay, so this series expansion contains only finitely many non-zero terms. Rest of the terms are 0. Okay, so that is a special case of this expansion, and that is called binomial expansion. Okay, so if m is a positive integer, then 1 plus x raised to m contains only finitely many terms. And what is the last term? Last term corresponding to fm of x. Okay, so what is the coefficient? What is the term corresponding to fm of 0? Corresponding to f2 of 0, this is x square by 2 factorial. So corresponding to fm of 0, the term is x raised to m5 m factorial. Okay, and what about fm of 0? In this case, fm of 0 is m factorial. So last term become x raised to m5 m by m factorial into m factorial. So that is nothing, our x raised to m. That's why here last term is x raised to m. Okay, so this expression is called binomial expansion, and this is valid for all the real numbers, because if m is positive integer, this function is continuous everywhere. Okay, so this is valid for all x. Okay. Another special case is m is negative. For example, m equal to -2 or m equal to -1/2 like that. Okay. In this case, what happened? Our function is like this. For example, m equal to -1/2. Our expression become 1 plus x raised to -1/2. That is equal to 1 by 1 plus x raised to 1/2. It is clear that this function is not defined when x equal to -1, right? So it is clear that if m is negative, this function is not defined at x equal to -1. Okay, so what is the interval of convergence in this case if m is negative for this series expansion? We know that interval of convergence of a Maclaurin series is always of the form mod x less than r. So that means we have to find a largest such interval such that this function is continuous. And we know that this function has a discontinuity at -1. So what is the largest such interval, or what is the value of r? Yes, we know that this length is 1. Okay, so the largest interval is mod x is less than 1. So this series is valid if m is negative. This series is valid only when mod x is less than 1. Okay. Similarly, if m is positive, there is no restriction for x, because if m is positive, this function is always continuous, so r is infinite. Okay, so combining all these cases, we define, okay, we can define a series that is called a binomial series, that is 1 plus x raised to m is equal to this series expansion, and this is valid in mod x less than 1, whatever be the value of m. If m is positive, negative, whatever be, no problem, this is always valid if mod x is less than 1. Okay, we know that if m is positive, this is valid for all x, but combining all these things, we can say that this is valid whenever mod x less than 1. So there is no restriction for m. You can choose any m. Okay, and this series expansion is called binomial series expansion. Okay, for example, find the binomial series of 1 by 1 plus x square. Okay, we know that the binomial series of binomial series 1 plus x raised to m is equal to like this. And here, what is the value of m? You can write this as actually 1 plus x raised to -2, right? So here the value of m equal to -2. So 1 by 1 plus x whole square equal to, you can expand using this formula. So 1 plus minus 2x, here m equal to -2, plus m is -2 into -2 minus 1 by 2 factorial into x square plus etc. And this is valid in the region mod x less than 1, right? Of course, here m is negative. So this is equal to 1 minus 2x. And what about this one? We can cancel 1, 2. So minus, this become minus of -3, right? So plus 3x square. What about the next term? Next term is -2, -2 minus 1, -2 minus 2 divided by 3 factorial, right? And you can expand this is like this. This is -2, -3, -4 by 3 factorial. So you can cancel 3 factorial, and minus into minus into minus again minus. So next term is minus 4x cube, right? Plus minus etc. And this is valid in the region mod x less than 1. Yes, so this is the binomial series expansion of 1 by 1 plus x square, and this series expansion is valid in the interval mod x less than 1, or this is the interval of convergence. Okay, next problem. Find the binomial series of 1 by square root of 1 plus x. And we know that binomial series is 1 plus x raised to m is equal to like this. So first we have to identify the value of m from this question. So we can write this as 1 by 1 plus x raised to 1 by 2, and this is equal to 1 plus x raised to minus 1 by 2. So what is our m? Yes, in this case our m is equal to minus 1 by 2. So now you can easily find the binomial series of this expression. So 1 by square root of 1 plus x is equal to 1 plus m. What is m? M is minus 1 by 2, right? So this is minus 1 by 2 x, plus the next term is minus 1 by 2 into minus 1 by 2 minus 1 by 2 factorial x square, like that. Okay, so this is the expansion. So this is m into m minus 1 by 2 factorial x square plus minus etc. Okay, and upon simplification this become like this, 1 minus 1 by 2x, and this expression become 1 into 3 by 2 factorial into 2 square x square plus minus etc. And this is the series expansion of this function, given function, and valid in the region mod x less than 1, because here m is negative. Okay. Okay, so next problem, find the Taylor series of 1 by x square about x equal to 3. Also we have to find the region of validity. Okay, we know that this is the formula for Taylor series about x naught. So either you can use this formula. If you apply this formula, then you have to find derivatives of this function at 3. Okay, then you can substitute. Okay, also we have another technique. You can expand this function about 3 using non-Maclaurin series. Okay, we have a Maclaurin series like this, 1 by 1 plus x square. We know its series expansion is 1 minus 2x plus 3x square, etc. And this is valid in the region mod x less than 1. Okay, in this case, I am going to apply this non-Maclaurin series for expanding the Taylor series of this function about x equal to 3. And also we know that the Taylor series of this function contains the terms x minus 3 and its powers, right? Taylor series about x naught contains x minus x naught and its powers. So here Taylor series about x equal to 3. So its Taylor series contains terms x minus 3 and its powers. So I'm going to convert this function in terms of x minus 3. How? So you can convert this function, given function. So this become, I'm going to subtract a 3, then neutralize the effect, we add a 3 to whole square. Then we have to find an expression in terms of x minus 3. So I am going to take this 3 outside. So this become 1 by 3 square into the remaining term is x minus 3 by 3 plus 1, right? So we can write this as 1 by, okay, this as 1 by 9 into 1 by 1 plus, okay, there is a square, sorry, there is a square. So 1 plus x minus 3 by 3 whole square, right? Okay, so our f of x is of the form 1 by 9 times 1 by 1 plus x minus 3 by 3 whole square. Now this is of the form 1 by 1 plus x whole square. The only difference is, instead of x, here our term is x minus 3 by 3. Okay, so what's expansion? Using this non-Maclaurin series, this is 1 minus 2 times, instead of x, this is x minus 3 by 3 plus 3x square. So x minus 3 by 3 square, we have a term outside, that is 1 by 9, right? We have a term 1 by 9 outside into like this. So minus plus etc. Okay, so this 1 by x square is equal to 1 by 9 into 1 minus 2 times x minus 3 by 3 plus 3 times x minus 3 by 3 whole square minus plus etc. Then what is the region of validity of this series expansion? We know that the region of validity of series expansion uh, of the binomial series is mod x is less than 1. So here instead of x, this become x minus 3 by 3. So the region of validity is modulus of x minus 3 by 3 is less than 1. Clear? This is equivalent to modulus of x minus 3 less than 3. So the region of validity of this series expansion is mod x minus 3 is less than 3. Okay, or this expansion is valid in the region mod x minus 3 less than 3. Okay. Yes. So this is the series expansion and valid in the region mod x minus 3 less than 3. So this is your homework. Thank you.